I'm Dhilung Kirat, and today I'll be presenting BareCloud, bare metal analysis-based evasive malware detection. This is a joint work with Giovanni, Vigna, and Christopher Kruegel from UC Santa Barbara. So, automated dynamic malware analysis is widely used to detect new malware threats. In this system executes samples in a controlled environment, monitors its behavior, and generates behavior profiles. So once we look into the behavior profile, we can see malicious actions. These systems are usually built upon virtualized, emulated, or heavily instrumented execution environment. However, there are many samples that try to detect this analysis system and stop showing their malicious behavior. These are called evasive malware. So how do they detect these analysis system? As in our previous talk, we saw a lot of techniques related to QEMU or emulated CPU. So basically, they try to detect components that are virtualized or emulated and that are part of the analysis system, such as trying to look for virtualized disk, virtualized BIOS, or maybe looking for some specific keyboard layout or presence of three-button mouse, or they can look for some user-specific information, such as username, some product ID that is related to some public-facing analysis system, such as Anubis, or they can look for the presence of active users, like waiting for an actual key press. Other type of evasion techniques include actually trying to detect the type of CPU that is being used to execute these malwares. One of the famous example is the red pill that checks the RDTR register and finds software-based execution environment. And with the emulated CPU, the problem is it's very difficult to accurately replicate all aspects of hardware CPU, as we see in our previous talk. So there are problems with implementation with the CPU, maybe with OP code exception, or maybe implementing other types of execute instructions, such as MMX instructions. So malware can detect these changes, detect these differences, and detect it's running inside an emulated environment. Other techniques may include actually using vulnerability that is present in the virtualization system. And finally, they can use timing-based attack, because the virtualization or emulation environment adds some level of overhead which can be detected during execution and used to detect this analysis system. Furthermore, these days, malware writers do not have to actually write all these evasive techniques. There are tools, so-called fully undetectable packers, that they can use to automatically add these features into their malware. So what are the solutions available? We can look for known evasive techniques in the behavior profile and see whether some malware is trying to evade or not. But that's pretty much like using some signature-based detection, which is weak and can be easily evaded. So another approach is actually trying to make the execution system more stealthier, or in other words, more transparent, so the malware doesn't see it. The idea here, so for example, instead of attaching a debugger, we can execute samples in an emulated environment and watch its behavior from outside. The goal here is to separate the execution environment and the monitoring component as far as possible without breaking the functionality. The idea is that when the malware execution, the monitoring component is far apart, malware doesn't see it. So we have better transparency. But this also works the other way around. When the malware component, monitoring component is far enough, there will be a problem with the visibility of the malware activity in the execution system. In fact, this trade-off between transparency and visibility has been a long-standing challenge in dynamic malware analysis. We want to have better visibility, then the system becomes less transparent, and when we want more transparent system, such as by executing in a real hardware, the visibility to the execution of this malware becomes poor. That is, we have less information to work with to understand the behavior of the malware. So at this point, we ask the question, can we automatically identify evasive malware under this reduced visibility? The idea is that we just want to identify whether a sample is evasive or not. We may have less information to actually understand how it's evading the system, but if we actually can detect that some sample is evasive, a malware analyst can always go back and manually analyze that to understand how they are actually evading the system. So to answer this, we present BareCloud. BareCloud is an automated evasive malware detection system based on bare metal execution. That is, samples are executed in a real hardware with no emulation, no virtualization, and most importantly, no in-guest monitoring component. This makes our system more transparent and robust against sophisticated evasion techniques, such as timing attack. Our system is implemented as a cluster of bare metal machines, which are controlled by IPMI-based controllers. We have LVM snapshot-based remote disk that is attached to all these bare metal system using I2C connections. And we monitor networks on the wire using network capture. And for the file system activity, we extract them from the LVM snapshot that is taken before and after the execution of the malware. We use SleuthKit to understand the operating system level file system details. So our system is more transparent, but we can see that we also suffer from the visibility problem here because we have only network-related and file system-related activities, but no process-related activities, such as process creation or memory read, memory write, and system calls, etc. However, we saw that even with this reduced visibility, we can actually detect evasive sample. For that, BareCloud also executes samples in other analysis environment, namely Ether, Anubis, and VirtualBox, and compares the behavior with a bare metal analysis system. Here, Ether is based on Gen hypervisor and uses hardware-based virtualization to make it more transparent. Anubis is QEMU-based. It's a whole system emulation analysis system. And VirtualBox is type 2 hypervisor. That is, the virtual machine manager is installed upon the host operating system. So once we have all this behavior profile, we'll compare their behavior profile with respect to the bare metal system. And the idea here is that if the malware evades one of these three systems, we see a difference in the behavior. And this way, we can detect evasion. For that, we need to compare the behavior profiles. So far, behavior profiles are treated as a list of events. And usually, some sort of set intersection-based method are used to compare behaviors, such as Hierarchical Similarity-based methods. However, if the events are interrelated, or if there is some structure within the events, this simple set intersection-based method may not provide optimal measure, similarity measure. To get an intuition, let's take an example. So here we have three profiles, profile A, profile B, and profile C, from the same malware when they were executed in different analysis environment. Profiles, they look similar other than the third entry of profile B and profile C are different. So let's calculate Hierarchical similarity between profile A and B and profile A and C. Turns out they are the same. But our intuition tells us that profile C is quite different because it's connecting to CNC server. So let's step back and try to analyze our intuition. How would we go about if we have two behavior profiles and we want to compare it manually? Probably we'll start asking questions such as, what type of events are available in this behavior profile? Do they have a file system activity? Do they have network activity? And then we move on to asking questions, are these events related to the same file name, same network path? And are they creating or deleting files, etc.? This kind of reasoning tells us that there is a behavior profile is not simply a list of events, but there is some internal structure, internal hierarchy within the behavior profile. To represent this hierarchy, we propose a behavior similarity hierarchy model, which is a simple tree-based structure with each level in which each level in the tree represents different abstraction level of the behavior. For instance, object type level represents type of the events that is available in the behavior profile. And the object name relates to, represents the name, such as file name or network endpoint of the event. So we can map the profile from earliest example into the behavior similarity hierarchy. Profile B can be mapped like this, and profile C. We can see that with profile C, there is another node in the object type because it includes both file type and network type events. So once we map all these behavior profiles into the hierarchy, the next step is to compare and find the similarity between these profiles. And I'll briefly explain the algorithm that we use. So the algorithm starts from the root and starts searching for matching nodes while traversing down. By default, the root node are considered matching nodes, and each level algorithm tries to find, identifies candidate sets. Here, the candidate sets is a set of nodes from the corresponding level whose parents are matching nodes. For example, in this layer, the candidate sets are highlighted because their parent, which is the root node, is a matching node. And once the candidate sets are identified, we compute Jacquard similarity and assign this intermediate similarity value to that particular layer, and move on to the next layer and find the candidate sets, and then compute the Jacquard similarity and assign this intermediate similarity to that layer, level, and so on. So once we have all the intermediate values, we compute a simple average of this similarity value, which represents the overall similarity between two hierarchical behavior profile. For this case, we have 0.79 with behavior profile A and profile C, and with profile A and profile B, it's computed at 0.87. So if we go back to our previous example, where with Jacquard similarity was giving us the same similarity, but using hierarchical similarity-based method, we have similarity between A and B greater than similarity between A and C, which was our initial intuition. So this algorithm gives us the similarity measure. However, we want to compute the deviation in the behavior. For this, we define behavior distance. The behavior distance is simply a complement of the hierarchical similarity. So it's simply computed by subtracting the hierarchical similarity from 1. And for each malware, we compute 3 different behavior distances corresponding to Ether, Anubis, and VirtualBox analysis with respect to a bare metal analysis system. Then we take the quadratic mean of these behavior distances to compute final deviation score, D, of the malware. Here, the deviation score, D, represents how the malware deviates from its execution when it's executed in bare metal system. And we also define deviation threshold, T. Here, deviation threshold, T, if the deviation score, D, is greater than T, we say the malware is evasive. To evaluate our system, we generated the ground truth. We received 234 recent and possibly evasive sample from a security company. We manually analyzed them and found out 111 out of 234 samples were in fact evasive. We use that as our evasive sample ground truth. For the non-evasive samples, we collected malware samples that were submitted to Anubis. We manually analyzed them in all 4 different environments and selected 119 samples which didn't show any evasive behavior in all 4 analysis systems. After that, we calculated the behavior deviation score D for all these samples. We also calculated Jacquard distance based deviation score JD, which is basically a maximum Jacquard distance among different behavior profile of the malware. So after that, we performed precision recall analysis by varying the deviation threshold T, and the result is presented in this graph. Here, the blue line in the graph shows the results when hierarchical similarity method was used, and the red line shows when Jacquard similarity-based method was used. So we can see that in terms of precision, hierarchical similarity measure performs better than the Jacquard similarity-based method. Here, but with the Jacquard similarity-based method, no matter how we change the threshold value, its precision didn't increase above 91%. While for the hierarchical similarity method, we could reach all the way up to 100%. So this 10% improvement in precision is actually pretty significant, because usually once we detect the sample is evasive, the next step would be to further analyze that by malware analyst. So with low precision or high false positive rate, that will waste a lot of precious time of the malware analyst, of the manual analysis. So when we plot the same result against the varying threshold value, we can see that when the threshold value is 0.84, we get highest precision with good recall. So in our next experiment, we use this value. So we performed a large-scale evaluation of our system. We used recent real malware feed that was observed by Anubis. However, the feed is too large for our system, so we randomly selected samples. I mean, we resampled from this malware feed from 4 categories. That is, samples that showed low system and low network activity inside Anubis, with sample with high system and high network activity, sample with high system but low network activities, and sample with low system but high network activity. With this filtering, we eventually analyzed 110,000 samples. Those were collected over a 4-month period, beginning from July 2013. And out of this 110,000 samples, BareCloud detected 5,800 samples as evasive. So out of this evasive malware, we can see that 84% of these samples were evading Anubis, 78% of the samples were evading Ether, 61% of the sample were evading VirtualBox, and 43% of the sample were evading all of these 3 analysis environments. So to conclude my talk, I point out that evasive malware is a real threat to the new wave of dynamic analysis-based malware detection system, and we presented a system that can detect this evasive malware automatically without any manual analysis. And with that, I conclude my talk. Thank you, and I'm open for questions.
So again, if you have questions, please come up to the mic and state your name and affiliation.
Hi, Grant Ho, UC Berkeley. So I have 2 questions. The first is, across your 4 system environments, what were the operating system versions, sort of library configurations? Like, were they consistent across all 4?
Can you state it again? I can.
Sure. So across like Anubis, Ether, and VirtualBox and your bare metal, were they all running on the same operating system? Did they all have the same libraries, and sort of what versions were they?
Yes, that is true. Actually, that is a very important point, because if we have different setup with missing DLLs or missing components, that will also generate deviation in the behavior. So we made sure the exact same internal software environment was present in all analysis systems.
Okay, great. And in terms of the 110,000 large-scale evaluations, so you said you found about 6,000 evasive samples. Mm-hmm. Did you check if any of these were sort of installers that required user interaction or automation to run?
We couldn't check all of the results, but we definitely did some random selection and analyze manually what was going on inside. To my experience, I didn't find any of them.
Okay, so all of them were sort of automated. You have high confidence that they were all malware?
So if we go back, like we choose the threshold value so that we have highest confidence to in our system that once we detect something as evasive, it is evasive. So obviously we don't have the ground truth for all the malware, but that gives the confidence level with the way we chose our threshold value.
Okay, and in terms of sort of the ground truth of that 110,000 sample, do you know how many approximately were malware, or is there any sort of guesstimation in terms of what that 5,000 out of 110,000 statistic means in terms of expected performance?
We can't be sure if it's really a representative, because if you remember, we did the pre-filtering after looking into the Anubis analysis system, but and usually Anubis receives malware as its input, but for now, like, I can't answer that question whether they're all aware malware or not.
Okay, thank you.
Thanks.
Hi, Christian Russell, Saarland University. I got 2 questions for you also. So I'm running a similar environment since 2 years, and one problem I encountered always is that there may be malware that are steady on the system even if you wipe the disk, because they implement themselves into the master boot record of the disk or into the BIOS even. Did you encounter such things happening?
We make sure we reset the BIOS settings after rebooting using the IPMI system, and so far I didn't find any, but I know like there are malware out there that does that. But for that, we can't do the differentiation between previous BIOS state and the resetted BIOS state.
Mm-hmm.
But yes.
Okay. The second question is about user simulations. I know that in Anubis you have some clicks that automatically click through installers. It's similar to the question before. Mm-hmm. Do you have similar simulations in now the VirtualBox environment and the Ether environment and your BareMetal environment, where you have basically a mouse or a keyboard pressing something?
Actually, so that was also a problem when we were comparing. So we removed that part from mm-hmm. the Anubis system. Okay. In our sandbox, we removed that automated installation, because that will mean we have to install something in our BareMetal system, which we did not want it to.
Okay, thanks.
Thanks.
Okay, thank you, Dhilung.
Thanks.
And let's thank him again.